The most important chip-making machine in China may not be the most advanced one. It may be the machine that was rejected, rebuilt, installed anyway, and improved after thousands of production failures. That is how a new semiconductor supply chain is being created, not through one dramatic breakthrough, but through a series of forced decisions inside factories across China. An imported tool becomes unavailable. A domestic supplier receives an order it would never have won before. The first machine performs badly. Engineers study every defect, redesign the system, and return with a better version. Then another factory installs it. More data arrives, more customers follow. By 2026, this process was spreading across chip-making equipment, memory, processors, software packaging, and AI data centers. America's restrictions were designed to deny China access to the technologies at the top of the semiconductor industry. But they also created something Beijing had struggled to build for years: guaranteed demand for Chinese alternatives. The blockade did not simply cut China away from the global supply chain. It gave thousands of Chinese companies a reason and a market to build another one. Before we get into how that happened, hit the like button and subscribe, because this is not a simple story about China replacing one NVIDIA chip or copying one American machine. The semiconductor industry is not controlled by a single country. American firms lead many processor designs, electronic design tools, and manufacturing equipment categories. ASML in the Netherlands remains the only commercial supplier of extreme ultraviolet lithography systems. Taiwan's TSMC dominates leading-edge contract manufacturing. South Korean companies lead major memory markets, while Japanese suppliers remain essential in wafers, chemicals, optics, and precision materials. What Washington controlled was a network of technological choke points. China could participate in global electronics, but advancement at the frontier depended on tools and services controlled by the United States and its allies. The response was not to reproduce the old supply chain exactly. China began building a parallel system optimized around the technology it could manufacture, the customers it could direct, and the enormous domestic market it could use as a testing ground. The controls were designed to make every step more difficult. Rules introduced from 2022 onward restricted advanced computing processors and the equipment required to manufacture cutting-edge chips. In December 2024, the U.S. Commerce Department added controls covering 24 categories of semiconductor manufacturing equipment, 3 categories of development software, and high-bandwidth memory used in advanced AI systems. It also added 140 entities to the entity list. In 2025, Washington closed a program that had allowed selected foreign-owned factories in China to receive some American equipment and technology without normal licensing. The restrictions reached deposition, etching, lithography, metrology, cleaning, design, memory, and assistance from technical personnel. The strategic logic was powerful. A fabrication plant is only as independent as its hardest component to replace. China did not need to lose access to every machine. It only needed to lose access to the machine that prevented the next production step. At first, the strategy appeared to work. Huawei lost access to the manufacturing partners behind its most advanced smartphone processors. Chinese fabs were prevented from buying EUV systems and faced tighter restrictions on advanced deep ultraviolet equipment. NVIDIA repeatedly redesigned products to remain below changing export thresholds, only to encounter additional controls. Chinese AI developers still depended heavily on CUDA, NVIDIA's software platform, while domestic chip makers struggled with production yields and limited supplies of advanced memory. The gaps were real, and many remain real today. But the restrictions also simplified the strategic calculation inside China. Depending on the best foreign technology was no longer always the lowest risk decision. A slower domestic component could become more valuable if it came with guaranteed delivery, local engineers, available replacement parts, and no threat of a future export license being revoked. The most efficient supply chain was no longer automatically the safest supply chain. That change in incentives became the foundation beneath everything that followed. Huawei's return to advanced smartphones provided the first major warning. When the Mate 60 Pro appeared with a Kirin processor manufactured by SMIC, using a process generally described as 7nm class, it did not prove that China had caught TSMC. The chip was likely more expensive to manufacture, less power efficient, and produced with lower yields. Without EUV lithography, SMIC had to push older equipment through more complex multiple patterning processes, adding masks, exposures, alignment steps, and opportunities for defects. But the phone proved something politically and industrially important. China could trade cost and simplicity for continued progress. Engineers had found a route across a barrier that was supposed to hold them several generations behind. The question was no longer whether China could produce an advanced domestic processor under restrictions. The question became whether it could support that processor with enough foundry capacity, equipment, memory, software, and customers to turn one breakthrough into a repeatable industry. SMIC is now becoming the manufacturing center of that emerging system. It remains restricted at the most advanced nodes and does not offer the leading production economics of TSMC. Yet the AI boom has created an unexpected opening. As overseas foundries redirect capacity toward AI accelerators, advanced memory, and high-bandwidth products, less glamorous chips used in appliances, vehicles, communications equipment, and industrial systems can become harder to source. In May 2026, SMIC said some foreign customers were moving orders back to China because capacity remained available there. China represented 89% of SMIC's first quarter revenue, but American customers still accounted for about 9%. Chinese foundries are also expected to increase their share of global legacy node capacity. This matters because a supply chain does not survive on flagship AI chips alone. It needs power controllers, display drivers, sensors, connectivity chips, microcontrollers, and thousands of ordinary components that keep modern devices operating. The next layer is the machinery inside those factories. Companies such as Nora, AMEC, Piotech, and ACM Research have expanded into deposition, etching, cleaning, thermal processing, and other critical production steps. Nora's 2024 revenue reached 29.8 billion yuan, approximately 5 times its 2020 level, while AMEC's revenue had quadrupled over a similar period. These companies do not yet replace every Applied Materials, Lam Research, KLA, Tokyo Electron, or ASML system. Their importance comes from where they are being installed. Once a Chinese tool enters a working fabrication line, it begins producing the engineering data that laboratory testing cannot provide. Weak components fail. Service teams learn where maintenance takes too long. Fabs identify which processes lose yield. Suppliers receive feedback, revenue, and another production cycle. The earliest machines do not need to become global leaders immediately. They need to become reliable enough to remain inside the line while the next generation improves. Beijing is accelerating that learning process through procurement. At the end of 2025, Reuters reported that Chinese chipmakers, seeking approval for new production capacity, were being pushed to source at least half of their equipment domestically, with flexibility where no credible local alternative existed. Applications that failed to meet the threshold could be rejected. The measure effectively transforms every new fab into a customer development program for Chinese toolmakers. Nora has tested etching equipment on SMIC's 7nm lines after gaining experience at 14 nanometers. Domestic cleaning and resist removal equipment has already achieved much higher localization than the most advanced lithography categories. The policy can impose real costs. Fabs may be forced to install equipment that performs worse than imported systems, reducing efficiency and yield. But the purpose is larger than one quarter's profit margin. It guarantees that Chinese equipment companies receive the orders, factory access, and failure data required to close the gap. The amount of money behind this process is enormous. SMIC reported that China spent approximately $49.3 billion on semiconductor manufacturing equipment in 2025, remaining near record levels and ahead of every other individual market. From 2026 through 2028, China is projected to invest about $94 billion in 300mm fabrication equipment, again ranking first globally. Not all of this spending goes to Chinese suppliers. China still purchases foreign tools wherever regulations and licenses allow. That dependence is one reason domestic replacement remains difficult. But every imported system is now entering a market where local alternatives are receiving greater political and commercial priority. Large spending also creates room for duplication. Several Chinese companies can attack the same category, use different technical approaches, and survive long enough for customers to identify which design works best. The result may be wasteful, but semiconductor development has never been cheap. Scale gives China the ability to absorb failures that would destroy a smaller national program. Memory is becoming another major pillar. China once depended overwhelmingly on foreign DRAM and NAND suppliers. By July 2026, Changshin Memory Technologies had become the world's fourth largest DRAM producer, while Yangtze Memory Technologies had developed into a major NAND supplier despite being placed on the US Entity List. The AI-driven memory shortage transformed their market position. Reuters reported that CXMT had gained enough leverage to raise prices, select preferred customers, and negotiate multi-billion-dollar arrangements with companies such as ByteDance and Tencent. It prepared an $8.6 billion Shanghai listing, the largest Asian IPO of 2026, after years of government-linked investment and operating losses. CXMT and YMTC still trail the leaders in the highest performance memory used for cutting-edge AI accelerators. But they have crossed the line from protected experiments into commercially powerful producers. A domestic AI chip becomes far more useful when domestic memory can be placed beside it. Huawei is building the computing layer above those factories. Its Ascend processors remain behind NVIDIA's best unrestricted chips in several important measurements, including memory bandwidth, software maturity, and performance per chip. But China no longer needs Ascend to defeat NVIDIA everywhere. It needs the platform to become capable enough for Chinese customers who cannot confidently plan around foreign supply. Huawei expected AI chip revenue to rise by at least 60% in 2026, reaching roughly $12 billion based on reported orders. Demand accelerated after DeepSeek introduced V4, which was adapted for Huawei's latest Ascend processors rather than being optimized first with American chipmakers. Alibaba, Tencent, ByteDance, cloud providers, and chip rental businesses reportedly moved to secure additional Huawei hardware. This was the moment the supply chain began closing its own loop. A Chinese AI model created demand for a Chinese processor, which created demand for Chinese fabrication, memory, packaging, servers, and software. The software connection may be more important than the silicon itself. NVIDIA's strongest advantage is not simply a fast processor. It is CUDA, the collection of libraries, tools, documentation, and developer knowledge surrounding NVIDIA hardware. Replacing that ecosystem is much harder than designing a chip. DeepSeek's decision to adapt V4 for Huawei changes the direction of development. Instead of creating a model around NVIDIA first and treating Ascend as a later conversion, engineers can build directly around the hardware available in China. Huawei's SuperNode systems then connect large numbers of processors so they operate as one computing platform. If each individual chip is weaker, the system can compensate with more processors, faster interconnects, workload optimization, and software designed around the limitations. The result may consume more electricity or require more cabinets, but availability can matter more than elegance when the foreign alternative is uncertain. China is also changing demand through policy rather than waiting for the market. In November 2025, authorities issued guidance requiring newly built data centers receiving state funding to use domestically produced AI chips. Projects that had not progressed far could be ordered to remove foreign processors already purchased. The measure created a protected customer base for Huawei, Cambricon, and other Chinese suppliers at precisely the moment they needed deployments, debugging data, and recurring revenue. Reports also indicated that regulators were discouraging major technology companies from ordering new NVIDIA products. This policy can reduce competition and force customers onto less mature hardware. It may increase power consumption and development costs, but it solves one of the hardest problems facing a new technology ecosystem: convincing the first major customers to accept inferior early products. Once domestic processors are deployed in real data centers, software teams have no choice but to improve them. The new chain extends beyond replacement. Huawei has proposed a different way to extract more performance from the manufacturing processes China can access. In May 2026, it introduced what it calls the Tau scaling law, focusing on reducing signal delay across devices, circuits, chips, software, and complete systems instead of relying only on smaller transistor geometry. The company also described logic folding, a method intended to shorten wiring paths and increase effective transistor density through circuit design. Huawei said 381 chips had been designed and mass-produced, using ideas associated with this approach over 6 years, and that a Kirin processor expected in autumn 2026 would adopt logic folding. These are Huawei's claims and future targets, not proof that China has built a leading commercial fabrication node. But they reveal the strategic shift. If China cannot follow exactly the same shrinking path as TSMC, it will search for packaging, architecture, interconnect, and system-level routes around the manufacturing gap. None of this means China has achieved semiconductor independence. ASML remains the only commercial EUV manufacturer and spent $4.7 billion on research and development in 2025 while continuing to improve its systems. China still depends on foreign technologies in advanced lithography, precision metrology, some design tools, specialty materials, high-end memory, and leading production processes. SMIC's advanced capacity remains constrained. Domestic equipment quality varies by category, and replacing mature foreign software can take years. Chinese firms may also recreate dependence inside their own supply chain if one protected supplier becomes dominant and stops responding to customers. The disagreement reported between Huawei and CXMT over memory pricing demonstrates that a domestic chain does not automatically become a cooperative chain. Once local companies gain market power, they begin behaving like powerful suppliers everywhere else, raising prices, choosing customers, and defending margins. America is still adjusting its strategy because a complete technological separation would also impose costs on American companies. In January 2026, the Commerce Department shifted NVIDIA H200, AMD MI325X, and similar processor applications to case-by-case review when specific security conditions could be met. At the same time, Washington continued closing diversion routes and tightening controls on Chinese companies and overseas subsidiaries. U.S. lawmakers debated additional restrictions on chip-making equipment, but scaled back parts of proposed legislation after semiconductor companies warned that overly broad controls could damage American suppliers without securing equivalent action from allies. This tension is built into export controls. Restrict too little, and China continues buying advanced technology. Restrict too much, and foreign customers disappear, revenue falls, and Chinese competitors gain a protected market. The policy can slow China's progress while simultaneously financing the demand that makes domestic substitution commercially possible. The strongest evidence that the balance is changing may be psychological. In July 2026, Chinese authorities were reportedly considering tighter export controls on their own advanced AI models, training data, and semiconductor designs. The proposals had not become final policy, and Reuters could not independently confirm every reported detail. But the discussion itself was revealing. For years, the semiconductor conflict was defined by China seeking access, while the United States decided what technology was too valuable to release. Beijing is now considering which Chinese technologies may be too strategically important to share with foreign companies. That does not mean China has overtaken the Western-led semiconductor ecosystem. It means the country increasingly believes parts of its own stack have become assets worth protecting. A supply chain that began as a defensive response to sanctions is starting to acquire offensive value. So did America's restrictions fail? Not in the simple sense. They denied China the fastest path to the most advanced chips, increased manufacturing costs, constrained output, and bought valuable time for the United States and its allies. But the controls also changed China's industrial incentives permanently. They turned domestic equipment into a requirement, domestic memory into a strategic asset, domestic AI chips into guaranteed purchases, and local software compatibility into a national priority. China did not rebuild the old global supply chain inside its borders. It built a new one around different trade-offs: more government direction, higher early costs, larger domestic scale, weaker individual components, and tighter integration between customers and suppliers. The chain is incomplete and still depends on foreign technology. But it is far harder to switch off than the system that existed before. America tried to control the points where China depended on the world. China responded by turning every one of those points into a market for something new.